Hello everyone, this is lecture 3 of course PE 645. In today's lecture we are going to deal with GLCM or gray level co-occurrence matrix, which is considered one of the second order features. Second order features are termed as such because they involve analyzing the relationships between pairs of pixels. In contrast, first order features would involve analyzing only the pixel values or intensity histograms. So in short, first order features deals with the pixel itself, while second order feature deals with the relationship between a pixel and its neighbor. GLCM or gray level co-occurrence matrix refers to statistical measures derived from the matrix that characterize spatial relationships between pairs of pixels with specific intensity values in an image. GLCM was demonstrated by Haralick and Shanmugam in the 1970s. So in GLCM, we are trying to make a tabulation of how often different combinations of pixel brightness levels or intensities occur in an image, considering pairs of pixels at certain spatial relationships, such as the distance and an angle. GLCM is well suited to analyze texture patterns in many applications such as medical image analysis. The term gray level in GLCM refers to the pixel intensities represented within a grayscale image. So we are dealing with the gray level, which is the value from 0 to 255. So we can consider that image is an 8-bit image. And the letter CM in GLCM refer to co-occurrence matrix, which is considered the core principle of it. It revolves around the analysis of spatial relationships among neighboring pixels. So we need to capture how frequently gray levels or intensities occur within an image. So we are trying to examine the arrangements of pixels in relation to one another. So we have an image and we are trying to find the relationship between a specific pixel and its neighboring pixel at a specific distance and angle, and then we are going to apply that for the whole image, and based on that, which is called co-occurrence matrix, to extract the features from that co-occurrence matrix. So as said, GLCM co-occurrence matrix, which is denoted by G, employs three parameters to facilitate its calculations. The first is distance, or D. It's a parameter which refers to the displacement between two pixels. Angle, theta, it refers to the direction in which pixel pairs are evaluated. This angle can be 0, 45, 90, or 135. And the number of gray levels denoted by N. This parameter indicates the number of discrete intensity values present in the image. And we are going to deal with these three parameters and try to change them and understand the effect of that. So as mentioned, GLCM works with gray levels, which is a value from 0 to 255. And the co-occurrence matrix in GLCM refers to the relationships between the neighboring pixels at specific distance and an angle. And we need from that co-occurrence matrix to extract the features. So we need to understand how to build the co-occurrence matrix first. Based on the specified three parameters, let's assume that we have a distance of 1, theta of 0, and we have a table or a simple image of values from 0 to 3. So we have n equals to 4. The first step is to create an empty matrix, which will be called the co-occurrence matrix, or in short, G. It should be n by n matrix. So we have now 4 elements, so it will be 4 by 4. So one can ask, why n equals to 4? Because in the gray level or the image, which is presented here, we have unique values of 0, 1, 2, and 3. So we have 4 unique values. After creating an empty n by n matrix, set the rows and columns like that from 0 to 3, and we need to understand before calculating the inner values of the co-occurrence matrix what theta refers to. So theta refers, as mentioned here, to the direction in which pixel pairs are evaluated. So we have now a reference here that can guide us where is the direction. So the angle starts from the right by 0 and it moves counterclockwise. So we have 4 known angles that are frequently used with GLCM. They are 45, 90, and 135. So now we understand the direction. So based on the direction and distance d, how to get the 2 pixels? We have initial pixel and we need to get the relationship between that pixel and its neighbor. So simply we can get that by the trigonometry projections based on theta. How can we do that? Simply if we have 2 lines and a theta between them, so we can get the perpendicular from that arrow in the y-axis and in the x-axis. So if this line has a distance of d, then this distance will be d cosine theta. So in the x direction, the distance will be d cosine theta, while in the y direction, we have d sine theta. Why are we doing that? Because in the table, we are moving left or right, upper or bottom, so we need to get the projections based on that theta. So after getting d cosine theta and d sine theta, we have a starting or initial point here called x and y. So the new position for the x direction will be x plus d cosine theta, and in the y direction will be y plus d sine theta. But this is correct if you are dealing with x-axis and y-axis in these directions. X-axis goes that direction and y-axis goes in that direction. But when we are dealing with tables in Python or any programming language or with images, we refer to the directions to be to the right for the x-axis and to bottom for the y-axis. So we need to change the sign from positive to negative in calculating the y direction. Based on that, we can get these 2 formulas to calculate the new direction or the target pixel based on d and theta. So here we have initial x plus d cosine theta, and for y will be initial y or current y minus d sine theta. And we are rounding d cosine theta and d sine theta because the indices or the places of the pixel should be integers. Assume that you are calculating cosine 45, it will be a floating number. So we need to round that number to be an integer. So let's get an example. If we have d equals to 2 and theta equals to 0, and we have an initial x and y in that color here with the coordinates of 1 and 1, then by using these 2 formulas, we can calculate x target and y target. So x target will be 1 plus 2 cosine 0 because theta is 0, and we are going to round that. Cosine 0 is 1, 1 multiplied by 2 equals to 2, rounded and added to 1 will equal to 3. And for y, 1 minus 2 multiplied by sine 0 which equal to 0, so it will get 1. So x and y coordinates for the target will be 3 and 1, which is here. What about dealing with d equals to 1 and theta equals to 45? By using the 2 formulas, we can get x and y for the target to be 2 and 0 respectively. So if you are placing in that position, the target will be here. Another 2 examples. If we have a theta equals to 135 and d equals to 3 and an initial place equals to 2 and 3, so the target by calculating cosine and sine for 135 will be 0 and 1, which is here. And when d equals to 3 with theta equals to 90, the new x and y or the target x and y will be 2 and 0, which is here. These 2 formulas are crucial when we are going to apply script or code using Python to find the neighbors automatically. So you are going to use these 2 formulas. So after understanding how to get the target position based on d and theta, we need to start to construct the co-occurrence matrix. So we have a table here with unique values from 0 to 3, 0, 1 to 3, so n equals to 4, and based on that we constructed the co-occurrence matrix, which is initially set to an empty matrix, and then we need to loop on each pixel in the image, and then for each pixel here we need to find the target x and y axis for the neighbor. So based on the given inputs d equals to 1, theta equals to 0, the direction, if we use the cosine and the sine, will be in that direction. This means if we got that pixel, the neighbor pixel of that pixel or the target pixel will be that. And if we are dealing with that pixel, for example, the neighbor pixel will be here. This is because we are dealing with the two inputs d equals to 1 and theta equals to 0. So after we get the pixel and the target pixel, we need to increment the co-occurrence matrix in these coordinates. What does it mean? We have here 1. So in the co-occurrence matrix, x will equal to 1, and 2, which is the target pixel, is y in the co-occurrence matrix. So you are trying to find 1 and 2 in that co-occurrence matrix and increment it by 1. So for x in that direction, we go by 1, and then in the y direction, we go by 2. So 1 and 2, we increment that place by 1. Then after that, we go to the next pixel, and the next pixel is 2. Then we need to find the neighbor for that 2, will be 3, based on the inputs d equals to 1 and theta equals to 0. Then we need to find x and y for the co-occurrence matrix, so we go at 2 and 3 and increment that field by 1. We do the same for the next pixel. So for x equals to 3 and y equals to 2, increment that field, which is here. And the same for the next one, 2 and 1. We increment that field. What about here? When we reach at a specific pixel and we get the target pixel out of the boundaries of the image or the table, we ignore that pixel. So for that pixel, the neighbor position will be outside the boundary. So we will ignore that one and move to the next row. So for the next pixel, x equals to 3 and y is 1. So we increment that pixel. We do the same for that, 1 and 2, and then we increment that field. It was 1 and we increment it by 1. It now equals to 2. We do the same and so on for other pixels until we reach the end of the table. After completing the co-occurrence matrix construction, which can look like that table, we can calculate the different features from that. But first, let's understand how to write a code to take an image or take a table, and based on that table or image, we need to construct the co-occurrence matrix. So here we have imported two packages, which is NumPy and Matplotlib. NumPy for numerical operations or arithmetic operations, and Matplotlib for visualization, as we are going to visualize the co-occurrence matrix. And then we defined d and theta with values 1 and 0 respectively, as we mentioned in the example, and we wrote the table in that format, which is considered a list of lists. Then that list of lists or matrix is converted to a NumPy array. Then how to get the value of n? To get the value of n, we simply find the maximum number in that matrix and add 1, because we have an initial value of 0. So 3 plus 1 will equal to 4 unique values. Then we construct, as mentioned, an empty matrix, which is co-occurrence matrix with dimensions n by n. Then we loop on each pixel in the matrix. This can be done using two inner loops, one for the x direction and another for the y direction. We get a starting location, x and y, and here we started by the y location because in NumPy array the indexing is reversed. It starts by the y location and then the x location. And based on theta and d values, we can get x and y for the target. We applied d cosine theta, d sine theta, and we don't need to forget that we need to add the round after calculating d cosine theta and d sine theta. Then we can get the end location. After that, we need to check if the target location is outside the boundaries. So, if the end location for x or y is less than 0, which is outside the left boundary, ignore and continue. And if the end location is more than the right boundary for x or y, ignore that boundary also. Then target is inside the boundary, so we have a starting location and a target location, so we need to increment the co-occurrence matrix by 1. As mentioned, we start by y, then x, so for the co-occurrence matrix, we start by y and then by x, and based on these two values, we increment the field by 1. And here, we printed what's happening, as we will see in the output. Then we printed the co-occurrence matrix, and then we visualized that using Matplotlib. When we run the code, this co-occurrence matrix appear. So here, our black, which is 0, and here is 1 equals to 4, and so on. This figure or plot will be beneficial when we are dealing with images, because images are much larger in size, and based on the output plot we can understand the relationships visually and the features also, as we are going to deal with. And as mentioned, we printed what are the steps. So for the starting location 0 and 0, with the end locations 0 and 1, increment x equal to 1, y equals to 2 in the co-occurrence matrix by 2. So you can write here any example or any table and test it manually and then verify it by code. So it will get you the different steps until the end, and then it will print the co-occurrence matrix for you. And to verify, the printed co-occurrence matrix is similar to the calculated one. And as mentioned, you can get another table and calculate the co-occurrence matrix for it, and then verify the results with the code. Once you have calculated the co-occurrence matrix, you can measure different statistical measures from that co-occurrence matrix that can characterize the texture and structure of the image or the table. These features are the energy or angular second moment, and this feature presents the order lines or uniformity of the image, and a higher energy value signifies a more uniform texture across the image. The contrast. This feature presents the local variations in the image. Higher contrast values signify the significant differences between neighboring pixels intensities. Homogeneity. It reflects the element proximity distribution within the GLCM to its diagonal. And regarding this feature and the diagonal word, we are going to understand that visually in a following example. Higher values of the homogeneity indicate a concentration of elements along the diagonal, which is an indication of a more uniform texture. Entropy. This value quantifies the randomness or complexity of the texture in an image. High entropy values indicate a more complex and less predictable texture, which can suggest greater variability in pixel intensity distribution. Correlation. This measure assesses the linear relationships between the pairs of pixels, and higher correlation values indicate a more predictable texture within the image. So for the entropy, the more the entropy, the less the predictable texture, while in correlation, higher correlation is more predictable texture. For this similarity, it calculates the average disparity in intensity between adjacent pixels, and the higher the dissimilarity values, the more or the greater diversity in the texture. So how to calculate each of these features? These are different formulas for each of these features. So for example, the energy. You are looping on each of the elements in the co-occurrence matrix, and you are getting each element and power it to 2 and sum all of these elements together to get the energy. And notice something here. Here we mentioned G and P. G for the co-occurrence matrix, while P is a normalized GLCM value. So to get P, we need to construct the co-occurrence matrix, and then we normalize all of the co-occurrence matrix by dividing each of the element by the summation of the co-occurrence matrix. And we are going to see that in the following slides. Another example, for contrast, we loop on each of the elements and multiply the normalized value by I minus j squared. I and j here are the indices of the loops, and the same for other features. So in our example, we have calculated the co-occurrence matrix, and let's assume for this moment we are not going to find the normalized version. We need to deal with these numbers as they are to facilitate the understanding of the formulas. So for the energy, we need to square each of the elements and sum all of them. So we will loop on each element here 0 squared plus 2 squared until we reach 1 squared and 0 squared. Then we sum all of these values to get 54. And for contrast, we multiply the value by the difference between the indices squared. So for the first, 0 minus 0 squared multiplied by 0, 1 minus 0 squared multiplied by 2, until we reach 3 minus 3 squared multiplied by 0 here. We sum all of these values to get the contrast value of 26. And for the homogeneity, we need to divide, as we see in this formula, the GLCM value by 1 plus the square of I minus j. So we start by the first pixel 0 divided by 1 plus 0 minus 0 squared, and for 2 divided by 1 minus 0 squared plus 1, and so on. And then we sum all of these values to get the homogeneity, which is 11.8, and so on for other features. So how to calculate the features using the code? So simply we built the co-occurrence matrix from the previous code, and then we started to calculate the energy. The energy formula is the square of each element, and we sum all of these elements. As we see here, the sum of the matrix is squared. So internally it will loop on each of these elements and square it, and then sum all of these values to get the energy. And for the contrast, we square the difference between the indices, which are here for the two loops, and then we multiply each of these squares by the corresponding co-occurrence matrix value, and then we sum all of these values to get the contrast. And for the homogeneity, we divide by 1 plus the square of the difference between the indices. And as you see here, for the entropy formula, there is a minus here, and we multiply the p-value by the log of that value. So we here multiplied the log of the co-occurrence by the same value, and we made a condition here to check if that value is more than 0, because if you applied log of 0, it's undefined, and it will raise an exception in Python. Let's get the dissimilarity first. As we see here, we multiply the value by the absolute value of the difference between the indices. So we here made the absolute value of the difference between the indices multiplied by the co-occurrence matrix at that indices. And then we calculated the dissimilarity. What about the correlation? As you see here, the correlation, we multiply I minus mu of I by j minus mu of j multiplied by the co-occurrence matrix value divided by sigma of I multiplied by sigma of j. Mu of I and mu of j are the means, and sigma of I and sigma of j are the standard deviations. I refers to the rows, while j refers to the columns. So we need first to calculate the mean, and to calculate the mean value for the x direction or for I and mean value of y direction or j, we simply multiply the co-occurrence matrix by I to get the mean of x, and multiply the co-occurrence matrix by j to get the mean value of y, or the y direction. We apply the same for the standard deviation. For the standard deviation, we subtract I minus the mean value, which is calculated here, squared and multiplied by the co-occurrence matrix. We do the same but for j to get for the y direction. After getting the means and the standard deviations, we can calculate the correlation. As we saw in the formula, I minus mean of x multiplied by j minus mean of y multiplied by the co-occurrence matrix value divided by the multiplication of the two standard deviations in x and y. By summing all of these values together, we can get the correlation. And here we made a square root because the resultant value of that summation is the variance. So the standard deviation is the square root of variance. By calculating all of these features, we then printed all of them here so we can get the output after calculation. If we executed the code, it will get the energy of 54, which is similar to here. The contrast is 26, which is similar to here. And the homogeneity is 11.8, which is similar to here. If you did the same for other features and compared it with these values, they should be equal. What about if we have an image and we need to calculate the co-occurrence matrix of it? As we did in the previous lecture, we calculated the first order features for a 2D image, just a single image, and a 3D volume that consists of different images. We will apply the same thing. We will first calculate the features for the 2D image, and then we will move on how to calculate the features for 3D images or volume. So here we have an image and the corresponding mask, and we need to calculate the GLCM features only for the ROI. So based on what we did in the previous lecture, we can get how to extract only the ROI and use that image as our table. So instead of defining the table by ourselves or the matrix by ourselves, we will replace it with ROI. So as you see here, we defined the code that we applied in the previous lecture that can find the cropped ROI for the lever only, and we can assume that cropped is our matrix, and then we can combine the calculations of the co-occurrence and the corresponding features in that code. And for simplicity, we made a function that can calculate the GLCM co-occurrence matrix and return it. And if we went to that matrix, it accepts our image, d and theta, and asks if you need to normalize the image or not, as we mentioned from a bit that we need to normalize the image or the matrix. So instead of we dealing with G, we need to deal with P. And another optional attribute is ignore zeros. So what is the benefit of it? Let's first loop through the code. We did the same in the previous code. We calculated n, we calculated the co-occurrence matrix, we looped and calculated the starting and ending locations. We checked if they are inside the boundaries or not. And here we incremented the location, and here we normalized the matrix by summing the calculated co-occurrence matrix by the summation of it. And here we added a very small value which is called epsilon to avoid any division by 0. So assume the sum of the co-occurrence matrix is 0. The division by a 0 will get not a number or is an exception. So here added a very small value. What about ignoring the zeros? To understand it, let's look at this figure. We have the lever, and this lever we need only to calculate the features of the neighboring pixels in that lever. So assume a pixel here and another pixel here. Do we need to get the relationship between that pixel and the neighboring pixel? No. What about here and here? No also. What about here and here? No. What about here and here? No. This is because we need only to find the relationships between the pixels involved in that lever only. So simply, to solve this challenge, we can check if the starting location or the ending locations are zeros, then ignore. So if the starting location is a value and we are going to find a target location here which is 0, then ignore it. What about here and here? Don't ignore. So to do that in the code, we find the intensity of the ending location if it's 0, and the same for the starting location if it's 0, then ignore and continue. And this condition will be validated if this optional attribute is true. So we applied here a condition to check if we need to ignore the zeros, and then we apply our check. And the same here. We will only normalize the matrix if this condition is true, which here is true by default. Finally, we return the co-occurrence matrix. After calculating the co-occurrence matrix, we pass it to another function called calculate GLCM features. This function encapsulates different features which we mentioned in the previous code, and then after calculating all of them, we return a dictionary of the different features, such as energy, contrast, including the mean and the standard deviation values. Then we printed each of these features and plotted the co-occurrence matrix beside the cropped image. So as you see here, this is the output. These are the different features where the contrast, for example, is 105.26 approximated, and the dissimilarity is 8, and so on. And if you see here in the visualization of the co-occurrence matrix, there is a distribution of the pixels here, and you can notice this distribution is around the diagonal. So if you return it to the definitions of each of these features, you can understand what's happening. So to ensure that the plot is correct visually, the GLCM should be symmetric along the diagonal as we draw here, and second, the diagonal dominance, where you might observe a concentration of high intensity values along the diagonal as you see in the figure. This indicates that similar gray levels are frequently neighboring each other, which is common in many natural images. To understand it a bit better, you can apply different d values and thetas and check, for example, the contrast and homogeneity, and return to the definition and check what's happening. So, for example, the contrast here, you would expect that the GLCM plot to reflect the degree of variation in the image texture. High contrast means that there are significant differences between neighboring pixel intensities, whereas low contrast indicates that neighboring pixel intensities are similar. So, for high contrast, the GLCM plot, as we see in the three plots, will show values spread out from the diagonal, indicating greater variation in pixel intensities. So, if you compare that figure with that figure, here we have a contrast of 327, here we have a contrast of 245, and we can say that there is a great variation in the pixel intensities and there is a spread out from the diagonal. There are pixels here, here, but not here. For low contrast values, the GLCM plot will show values concentrated close to the diagonal, indicating similar neighboring pixels intensities. So in short, higher contrast images will have more spread out and varied values, whereas low contrast images will have values more concentrated around the diagonal. Second, for the homogeneity, in a GLCM plot of a homogeneous texture, you should see higher values concentrated along the diagonal line from the top left to the bottom right. This concentration indicates that pixels with similar intensities are more frequently neighboring each other. So, for a homogeneous texture, you would expect that the GLCM plot to show a concentration of values along the diagonal. This indicates that pixel pairs with similar intensities are more common, which is characteristic of a homogeneous texture. The values shouldn't be widely spread across the matrix. If the plot shows values scattered far from the diagonal, the texture is likely not homogeneous. So as you see here in these two values, this image is higher in homogeneity because the values are not scattered far from the diagonal. You can notice the meaning also by trying different images and capturing the contrast and the homogeneity of them and putting them together and say, yeah, this image has scattered values from the diagonal, this image is not, and then you see the values, and these values can get also an indication if you are correct or not. In this code, we will make a simple modification to the function calculate GLCM features to make it a bit faster, because when you will execute the co-occurrence matrix and the features for a large image, for example 124 by 124, it will take a long time. This is because the for loops, the more the size, the more the time. So we simply, instead of building multiple for loops, we can combine all of the features inside only 2 for loops. So for example, in the old code, here we apply 2 for loops and here we apply another 2 for loops. So we can combine both of them together as we see here inside a single 2 for loops. We can do that for all of the features, but for the standard deviation and the correlation, we need to split them, because the standard deviation will depend on the mean and the correlation will depend on the mean and standard deviation, so we need to calculate each of them separately. And also here we returned them as a dictionary. If you compute the time for the previous code and this code, you can notice that it's a bit faster. Here we are going to introduce a package that contains 2 functions, gray comatrix and gray coprops. These 2 functions calculate the co-occurrence matrix and features for a single image. This package is called scigetImage. So simply we have loaded the cropped ROI, we calculated n and defined d and theta, and to execute that function to get the comatrix, we called the gray comatrix, applied the cropped ROI, defined the distance, defined the angle, defined the levels, defined that we need it to be normalized, and we need to set it to non-symmetric. Then there is something missing here, which is the ignorance of zeros. To ignore the zeros, we know that the zero starts as a matrix or co-occurrence matrix. So simply we can skip it by indexing. So here we calculated the co-occurrence matrix, and here we skipped the first row and the first column, which indicates the zeros. So we are passing here the co-occurrence matrix after skipping the zeros, and if you don't need to skip the zero, you can simply remove that highlighted portion. Then we pass to the function gray coprops and pass the property, which is contrast, correlation, energy, homogeneity, ASM, and then we printed it. Notice here the energy and ASM. And if you remember, when we define the different features, we said the energy or ASM, the angular second moment, are similar. But here in this package, they are differentiating between both of them. They are getting the energy as the square root of the angular second moment. But in both cases, it will not make a difference, because if you are going to calculate this feature, energy or the angular second moment, for many images, all of these images will get the square root. So there will be no difference by applying a square root or not. And this package offers only these features. Then we plotted the co-occurrence matrix, and here we also skipped the zeros. After executing the code, this will be the output of the scigetImage package, and this is the output of our implementation where we saw from a bit. If you compared both results together, you will find they are similar. This is the contrast, 105, here the contrast, the correlation, the energy, the homogeneity, and the angular second moment. And you will notice that the energy here is different than here because they are differentiating between the energy and the angular second moment. So our energy value is similar to the angular second moment. And as mentioned, it will not make a difference or a big deal. Also, if you look to the figure here and here, they are similar. What about if we didn't ignore the 0 here and plotted the figure? Let's first notice that the zeros construct a large portion of the image. So if you executed the code, you will notice that you are getting black image, but it's not black. If you zoomed in that part, you will find that it's white here for the 0. This is because we said there is a large portion of zeros. So the 0 value will get the highest value in the co-occurrence metric, and by dividing and normalizing the image by that highest value, all of other values will be very small. So as you see here, they appear in black. So what about dealing with a volume? How to calculate the GLCM for a 3D volume? There are different approaches to do that, such as calculating the GLCM for each of the images and then taking the average of them. But this approach will ignore the neighbors in the z direction. But the approach we are going to deal with will be much similar to the approach we dealt with in the 2D image. In the 2D image, we assumed we have a theta and d or r in our example here, and we calculated the perpendicular in the x and y axis using cosine and sine, and we got the direction to be x plus rounding of d cosine theta, and y will be d multiplied by sine theta, as we saw in this portion and in this portion. But now we have another dimension, which is z. So assume we have a point here, and we need to get the target point, which should be, for example, here in another image, and we need to get the coordinates based on d and theta. So to do that, we can get benefit from the spherical coordinates. So assume from that figure we have x, y, and z, and a point that starts from the origin, and we need to get p here based on two angles, theta and phi. Theta is the angle between the perpendicular of the vector p and x-axis, and phi is similar but for z-axis. So simply, if we need to get the perpendicular of p along the z direction using the phi, we simply get the perpendicular using cosine. So we have a vector here, we have a theta, so the perpendicular will get cosine phi. So the distance from z will be cosine phi. And here they defined rho in the figure, and in our equation we are defining it as a d. So for the z target, it will be the current z and plus round of d multiplied by cosine phi. What about x and y? If we got a perpendicular in the direction in the xy plane, it will be sine phi. So this perpendicular is rho sine phi or d sine phi. So we need, based on that and theta, we need to get the direction in x and y. So for x, it will be z value multiplied by cosine theta, and for y will be z value multiplied by sine theta. So for x, it will be the current x plus d or rho cosine theta, which is here, multiplied by sine phi. And for y will be sine theta multiplied by sine phi, which is here and here. But if we assume that theta and phi are similar, then we will get these three formulas. X will equal to the x current plus round of d cosine theta multiplied by sine theta. And for y will be sine theta squared. And for z will be only d cosine theta. And here we are determining that it's here plus, here minus, and here plus, because we said for the images, this is the x direction, this is the y direction, and this is the z direction. So we need to get the opposite of y. That's why we added here minus. So we now know how to calculate x, y, and z. And we have a volume of ROIs. These ROIs shouldn't be similar in width and height. So for these three ROIs, you will notice that they are not similar in the width and the height. See here and here, different heights, here and here. And if we tried to combine them in a volume or a matrix using NumPy or any approach, it will raise an error that says they are not similar in the shape. So simply we can add padding for the different directions to unify the width and the height for all of the images to construct the volume, and we need to keep the lever or the ROI or the region of interest in the center. So if you notice when we padded that portion of lever, you will notice we added a black region here or padding and a black padding here, same here and same here. So how to do that? In this code we have defined three slices that constructs a volume. Then we defined d and theta, and we are dealing that theta is equals to phi. Then we made a function to read a volume and returns the ROIs as a volume and apply padding. How did we do that? We looped on each of the images with the corresponding masks, and we got the ROI and appended it to a list here that's initially defined with an empty list. Then to get the padding or unify the width and the height, we need to get the max width and max height. So we loop on each of the cropped images in this list, and we got the maximum value of the widths to get the max width, and the same for height. Then we looped again for each of the images or the ROIs in that list, and we got the difference for each of the images between its shape and the maximum width and the height. So for example, the difference between the maximum width and the current shape will get a delta value that should be filled with padding, and the same for height. Then we apply the function called copyMakeBorder, which is available in OpenCV package. We defined the ROI, we defined the padding in the height from the top and bottom. Here we split the delta in two portions, one for top, one for bottom, similar to left and right, and we said we need to apply a constant border with a value of 0 to be black. After that, we copied the result to replace the old ROI with the new padded one. After that, we made the volume or the matrix and returned it. After reading the volume, we have it as a matrix or volume. Then we created a function that mimics the 2D image to apply and get the co-occurrence matrix but for 3D with the same parameters. Here we did the same, but instead of using only 2 for loops, we applied 3 for loops because we are dealing with 3 dimensions. And as we said, the dimensions are reversed. So z starts, then y, then x. We applied the formulas and got the end location. We applied the condition that it checks we are inside the boundaries. Then if we need to ignore the zeros, if we need to normalize, and we need to increment the co-occurrence matrix similar to the 2D image. But here we made a small change. Instead of creating n by n matrix, we need to create n by n by n volume. But notice that for each of the images, the values in each of them will be from 0 to 255. But the number of slices in the volume doesn't have to be from 0 to 255. Then we have here defined the initial width and the height to be n by n. But for the z directions, we only specified it as the number of slices. So if we have only 3 slices, as in our example, we don't have to create an extra 252 empty matrices. Another advantage of it is the processing. If you are processing, for example, n by n will equal to 255 by 255 by 3. If you are defining here the number of slices to be 3, it will be this number of iterations if compared with n by n by n. So it will get a benefit of reducing the iterations time. After getting the co-occurrence matrix, we calculated the features by defining GLCM feature 3D. It's similar to GLCM features for 2D, but here we applied, instead of 2 loops, we applied 3 loops. Then we return it as a dictionary, and here there is an extra 2 elements, which is the mean z and the standard deviation z. Finally, we printed the results. If you executed the code, we will get the following results. For example, the homogeneity will be 0.06 and the dissimilarity will be 16.58 and so on. Finally, to facilitate for you to access the different scripts and codes alongside with the videos, I'm sharing with you a public GitHub repository which can be accessed using that link. So you can access the different scripts using this folder. You will find the different scripts here alongside with the sample images and volumes. You will find the full playlist also here, and the different videos will be added also here as links to YouTube. And you can clone this repository if you know how to, or simply you can press on code, download the zip file and extract it, and you can use the different scripts in it.